Hey everybody, today we're going to be doing a little bit of an induction proof involving the product, and all we have here is that m factorial divides the product from 1 to m of n plus I for all n and m in the natural numbers. I'm considering the natural numbers to be not including 0, but technically n could be any other negative number. It doesn't really matter, but m should just be restricted to greater than 1, but a natural number. So remember, divides notation just means that this divided by this will give us an integer, so that's what we're trying to prove. Now you might think we might do the induction on n, but we're actually going to be doing it on m, because that's what we're kind of dealing with. N is kind of just a constant here. It makes it a little more difficult because if I didn't have an n and it was just I here, that's really easy because all this is n factorial, and n factorial divided by n factorial is just 1, so it's a pretty trivial problem at that point. But here, this makes it a little more difficult because you can't really solve it through just manipulating it through factorial notation and whatnot. You can try, you won't really get far, but this way we have to kind of basically do it by induction. So let's start. So we have a proof here, so proof, and I'll just make it clear that we're doing it by induction. And so the base case is pretty easy. We're going to start with m equals 1. So base case, okay, so m equals 1. So when m equals 1, that means the starting and the ending value is the same, meaning we're just left with n plus 1. That's it. So we have and I'll just do it this way, so n plus 1 divided by m factorial, and m, like I said, is 1, so we can just replace that with 1 as well. 1 factorial is just 1, so this is equal to n plus 1, and since n is an integer, then n plus 1 is also an integer, specifically a natural number, and that's it, so that was easy. And so now for the actual induction step. We have basically the same sort of setup. We're going to assume that this works for m equals k, that this claim is true for m equals k, and then we're actually going to prove it for m equals k plus 1. So let me kind of do the same setup. I will multiply by the factor of 1 over m factorial out front, and again, m here is equal to k plus 1, so this is k plus 1 factorial, and then I'm going to multiply by the product from I equals 1 to k plus 1 of n plus I, and then basically we can rewrite a couple of things. First of all, the k plus 1 factorial, we can think of that as k factorial times k plus 1, okay, because whenever you take k factorial multiplied by k plus 1, then that's like that extra term, so k plus 1 factorial is the product from 1 times 2 times 3 all the way to k minus 1 times k plus 1, and really if you remove that last k plus 1, you just get k factorial back. So I hope that makes sense. And then this product, we can split this up into the product from I equals 1 to not k plus 1, but just k of n plus I. And then what that means is we have to multiply by that last term, that k plus 1th term, and I'll just do that up here since we have space. And so this is going to be n plus I would be k plus 1, so n plus k plus 1. And then from here, well, we know that this product here is divisible by k factorial because that is our induction hypothesis. So we know that part's true. What about this last part? What about n plus k plus 1 divided by k plus 1? Well, we can kind of break this up into n over k plus 1 plus k plus 1 over k plus 1, right? I just basically took this first part and then the second part and kind of just split that up that way. This is just equal to 1, so all this is n over k plus 1 plus 1. And k plus 1 is just m, so in general what this is n over m plus 1. And so we need this to be an integer, right? 1 is an integer, so we need to make sure that n over m is an integer. And that's specifically, we're talking about natural numbers. So actually, we could talk about integers if we let n be negative. That's okay. Problem is n doesn't always divide m. So this shows that for all n doesn't actually work, right? It doesn't work for all n. So let me take my blue marker here. This works for all m in the natural numbers, definitely. It also works for all n such that m divides n, right? So that's the real condition. So I kind of wanted to show you a little bit of a disproof, but as long as we have this condition such that m divides n, in other words, n over m is an integer, then this works. So if we assume this part, then this little product here works, or this little portion here works, right? So that's an integer. And then by the induction hypothesis, we were able to show, or we assumed that this product here, this product divided by k factorial, that's also an integer. So I made this picture a little ugly here, but so now pretty much we know that this whole thing is an integer, so it works. So this is the real proof. So we had to modify the claim just because originally it wasn't actually fully accurate. So this is kind of, I just wanted to give you a little exercise in showing like a disproof and then being able to modify it to make it a real proof, right? So I hope you enjoyed the video. Thank you so much for watching, and I'll see you in the next one. Bye guys.